I am going to thank Senator Colbeck for inviting me here. And why can we expect a wide variety of diseases from electromagnetic radiation exposure? First thing is that there is truly a wide range of opinions about what limit of radiation is appropriate. The FCC is there. Sorry, it's a bit of a shake. 10 million. But at 920,000, you have inhibition of DNA repair in cells. China, Russia, Italy, Switzerland are at 100,000. Karyotype changes in cancer cells, I will show that. Those are my personal experiments at 24,000. Permeability loss of the blood-brain barrier around 4,000. Bioinitiative Salzburg resolution recommendation about what is safe, 1,000. And of course, below that, you have the building biology recommendation. Those are essentially people who make recommendations for people who are already sick from radiation, who recommend that you have 0.1 microwatt per square meter. That's very, very little, isn't it? But the natural background radiation is 0.0000001 microwatt per square meter. So the big question is, are we adapted to the environments that are created by industry and by technology? They're very different from what we had naturally. So a bioeffects summary is that if you look at the literature on its whole, you see enormous numbers of reports of altered enzyme activity, biochemical changes, oxidative stress, pathologic changes in cells, neurobehavioral effects, DNA damage, altered gene expression, brainwave changes. So the evidence is there that a lot of things are occurring. But what do these things mean in practice? Does it indeed make us sick? So this proves that the results that I will report to you, which are the results of my own personal experiments, is compatible with a large body of evidence. Essentially, it's nice to read articles, but when you see the results in your own lab, under your microscope, and you make your measurements, you become increasingly convinced and increasingly responsible as to this situation. So in my experiments, I use levels of exposure that are similar to the ones that you're exposed to. Most reports on effects use very high levels of radiation because in toxicology, we increase these levels very, very highly in order to get results very, very quickly. The second thing is that in my experiments, I contrast a pre-industrial environment with what we have now. In other words, I bring the cells back to the 1900s when there was no low-frequency magnetic fields, there was no RF frequency radiation. And in my test, I'm very careful to precondition the cells at least a month before I perform the experiments so that I'm not looking at something that is changing in these cells progressively. I have tested the reactions of all major human cancer cells. And the tests that I run are run with low-frequency fields, but they are relevant to telecommunication signals because these signals always contain low-frequency components. My results show that you have clear effects on cancer cells at levels that are at least 500 times below the FCC recommendations. These fields suppress metabolism. They are what we call a metabolic disruptor. They probably make us a bit fat. We attribute this to, lifestyle, all sorts of things. I am saying that the fields make us fatter. So the question is, will American women forgive industry for making them fat? So the fields are disruptive, but so are changes in the fields. And I cannot assess this at all scales of time. It would be very, very expensive. But my results show that these fields are more disruptive to cells than oxygen. And as you know, when you consume oxygen in your cells, you generate what is called reactive oxygen species. Also, these fields increase necrosis. They augment the rate at which cells die, creating inflammation. So if you look at this slide, the red lines at the top for each of these major cancers, breast cancer, lung cancer, colon cancer, leukemia, all of this data should be at the top where the red line is. According to the magnetic fields that I applied, and these fields are relevant to your environment that you're subjected to in your home, these cells lose chromosomes. These cancer cells lose chromosomes. And this is not something that is statistically insignificant. It's very, very clear. A cancer cell that has fewer chromosomes can be more dynamic. So at the very left of the diagram, you would have the pre-industrial situation that should be at the top of the diagram. And if you want to know what these fields correspond to in the general environment, the red lines at the bottom explain that. Now, the cells over time adapt to the fields. And this diagram is a bit complicated, but what it says is that if you look here at the very left, this is the baseline. You apply the field. 3 weeks later or 4 weeks later, the cells have recovered. It takes them that much time to recognize the influence of the field itself. Once you are at this higher field level, and this is what the lower diagrams show here, this one and this one, if you then change the field even minutely, you again have an effect on the cancer cells. So as you can see, your cells do adapt over time by this variable, but they are sensitive to the fact that the fields change. Now let's talk about reactive oxygen species that I mentioned earlier. And in contemporary biological thinking, reactive oxygen species are of great importance. Essentially, they became into prominence very many years ago when Denham Harmon pointed to them as being a primary cause of aging. And you can see here that they influence necrosis, apoptosis, aging, disease, mitochondrial dysfunction, and so on. And the site at which these perturbations occur are in the mitochondria, which are small organs in your cells that are electrically incredibly active. Mitochondria work at 1 voltage well. It's 139 millivolts that will relate to the engineering community. If you change this voltage by as little as 2%, you will generate more reactive oxygen species, either less mitochondrial voltage or more. Both of them will generate more reactive oxygen species. So this is the result of a bunch of experiments. There are 150 one-week experiments in which I compare the damage done by sudden influx of oxygen to the damage done by sudden influx of electromagnetic fields. And in these experiments that I compiled over many, many months, I find that magnetic fields are more powerful than oxygen in generating reactive oxygen species. So in the body, you have many, many sites where, in the view of modern biological science, reactive oxygen species perform harm. Practically every important, I would say, system in the body is influenced by this. And to just give you an idea, diabetes, heart disease, Parkinson's, Alzheimer's, multiple sclerosis, ALS, psychiatric disease, reproduction, and autism. Those are all things that we know from I just placed a few examples here from the literature that reactive oxygen species enhance these diseases. So this is a very significant situation. Now, what about 5G? How is 5G going to change things? Well, it's going to change things by increasing the data transmission rate. There's an equation here that gives you the capacity. The problem with IoT is that it assumes that there is a constant noise in the environment, which is not entirely true. So when we have lots of radiation, perhaps the data transfer will become a little more difficult. And to explain why 5G does require higher powers, you can see here that the antenna aperture in the higher frequencies is not as high as it is with lower frequencies. So radiation at 5G diffuses according to a spherical pattern, and it also needs more power because the wavelengths are very, very much smaller, so you get less energy. And of course, this radiation does not penetrate as deep in the human body because of its frequency. It concentrates more on the surface. What does 5G look like? Well, it's not a radiator that goes in every direction. It's very concentrated beam, as you can see this. And this is achieved by a pattern of dipoles that can be steered like a gunshot in various directions. And so Tom Wheeler would like you to believe that this is incredibly innovative technology. But as you can see there, it is a very old technique used first in the MiG-31, the Zaslon radar, that was used by the military and that is being simply transferred in the telecommunications industry. And so what we're trying to avoid is a situation in the future in which the telecommunications industry will be in the same situation as the asbestos industry, which was essentially made completely bankrupt. Anybody who touched asbestos went bankrupt as a result of liability suits. We don't want the same thing to happen. We want to work with industry to make this technology safe. It can be done, but we need that engineers believe that the effects are real. If they do, there's all sorts of ways. Engineering is nothing if not flexible. If you go on the Starship Enterprise, Scotty always pulls through. The ship never explodes. We can do this if we do it together. Thank you.